Now we know how intermolecular forces determine things like viscosity and surface tension. And we also know that the kinds of intermolecular forces a substance can participate in will determine the phase that a substance will be in at a particular temperature. This means that we will want to understand what is going on during certain phase changes. For example, let's think of the temperature at which a liquid changes between a liquid and a gas. If going from liquid to gas, this process is called vaporization. If going from a gas to a liquid, this process is called condensation. The key thing to understand is that in the liquid phase, the molecules are in constant contact and are therefore participating in whatever intermolecular forces that substance is capable of. In the gas phase, the molecules are far apart and are not making such interactions. So a change from one phase to the other involves either breaking or forming these intermolecular attractions. If we look at a liquid in a closed container, we must understand that some molecules at the surface of the liquid may spontaneously vaporize, entering the gas phase. This will happen even far below the boiling point of the liquid. And if a molecule in the gas phase collides with the surface of the liquid, it might condense and re-enter the liquid phase. If these two things are occurring at the same rate, we have a dynamic equilibrium between the liquid and gas phases. This is a situation where nothing appears to be changing, but the word dynamic implies that change is still occurring, just with equivalent rates. So the amount of liquid and gas do not increase or decrease. The pressure exerted by such a dynamic equilibrium between liquid and gas is called the vapor pressure of the liquid. The surface area of the liquid will not affect the vapor pressure, but it will affect the time it takes to reach dynamic equilibrium, as less surface area means it will take more time for molecules to find the surface of the liquid. We can measure the vapor pressure of a liquid using a closed-end manometer, as the vaporized molecules will push down on the mercury, resulting in a measurable pressure. The stronger the intermolecular forces in a liquid, the lower the vapor pressure will be, because particles will be less likely to escape these attractions and will also be more likely to rejoin the liquid if vaporized. If there are only weak intermolecular attractions, many molecules can escape the liquid phase, which will generate a greater vapor pressure. Vapor pressure will also increase with increasing temperature, as more kinetic energy gives molecules a greater likelihood of escaping the attractions. And this means more molecules will vaporize, thus increasing the vapor pressure. And now we can associate phases of matter with intermolecular forces.